Welcome to Hartman Math. This is lesson 5.1, using fundamental identities within trigonometry. So we're extending our knowledge of trigonometry. We begin with the reciprocal identities, which say that sine of u or theta or x, whatever, is equal to 1 over cosecant u, and cosecant u is the reciprocal of sine of u, and so on. We've got quotient identities that the tangent of u is sine of u divided by cosine of u, and then if we do the reciprocal on both sides, we get cotangent u is cosine u over sine u. Very important Pythagorean identities, all stemming from sine squared u plus cosine squared u equals 1. We can algebraically manipulate that. If we want to solve for sine squared u, we get sine squared u equals 1 minus cosine squared u. If we divide by cosine squareds, we get this one. If we divide this by sine squareds, we get this one. And we can also manipulate both of those. So really there are a total of 9 Pythagorean identities if you look at all the manipulations. Co-function identities, which say that sine and cosine are co-functions, tangent and cotangent are co-functions, secant and cosecant are co-functions, and what it means is that the cosine of an angle is equal to the sine of its complement. So co-functions of complements are equal. So if we were to think of that in degrees, it would mean that the sine of 40 degrees is equal to the cosine of 50 degrees. The tangent of 20 degrees is equal to the cotangent of 70 degrees. The even-odd identities, sine and its reciprocal, tangent and its reciprocal, those are odd functions such that the sine of the opposite of an angle is the opposite of the sine of the positive angle. Same thing over here. Cosine and its reciprocal, however, are even, where the sine of the opposite of the angle is just the cosine. The cosine of the opposite of the angle is just the cosine of the angle. So example number 1, use identities, and we're going to follow those directions because there are other ways of approaching a problem like this, but we're going to use the identities to come up with the other 5 trig functions. We know that the cosecant of u is 5 over 2, and then a clue that says the tangent of u is less than 0, therefore negative. That's going to tell us what quadrant u is in, and that's going to be important for the signs of sine, cosine, tangent, etc. So the first one I would think that we would go with here would be reciprocal. That would be easiest, and say, well, if the cosecant of u is 5 over 2, and that's going to tell us that the sine of u is 2/5. Now, what quadrant are we in such that sine and cosecant are positive? That's quadrants 1 and 2. But tangent is negative. That's got to be quadrant 2. So as we make our other decisions, keep in mind that we're in quadrant 2. Now, for a Pythagorean identity, if we're looking for cosine, remember that sine squared u plus cosine squared u is equal to 1. Therefore, cosine squared u is 1 minus sine squared u. So that's our notation for sine of u squared. We don't say sine u and then squared because that would indicate squaring the u. This means sine of u squared on the outside. Okay? And this is the way that we use the notation, sine squared u. So it means 1 minus 2/5 squared, that's going to be cosine squared u. So that's 4 over 25. 1 minus that is 21 over 25. Take the square root. But knowing that we're in quadrant 2, that is going to make cosine negative. Now that we have sine and cosine, we could use a quotient identity and say that the tangent of u is sine divided by cosine. And if we do that, although they're complex fractions, the over 5 and over 5, they're just going to cancel. So we're really going to get 2 over negative root 21, or negative 2 over root 21. We also have the reciprocal there. The tangent one that I was just talking about, its reciprocal, cotangent of u is negative root 21 over 2. So we did a reciprocal, we did Pythagorean, we did quotient. We used quite a few identities. Example number 2, simplify the expression. So we might want to do some algebra such as factoring. So we could factor out a common factor of cosine theta, in which case we'd be left with sine squared theta minus 1. This is very close to one of our identities. We do have an identity for 1 minus sine squared theta. So the reverse of that, the opposite of that. So what we can do there is to reverse it, is to do that opposite, factor out the negative. Factor out the negative. Now for this, 1 minus sine squared theta, that's cosine squared theta, Pythagorean identity. Multiply these together, we got our final answer, negative cosine cubed theta. Example number 3, factor. It's a difference of squares. Part B, factor. Well, everything's in terms of cotangents, so I think we're going to do as a product of two binomials. So what in the front could make 6 cotangent squared x could be 6 cotangent x and 1 cotangent x, or 2 cotangent x and 3 cotangent x, with a plus 5 in the back, so that we're going to have multiply two numbers to get the positive 5. But when we do outside inside, we're going to get negative 13 cotangent x. And I think what works is 3 cotangent x minus 5, 2 cotangent x minus 1. If we check, we're going to get negative 3 cotangent x and negative 10 cotangent x. Does make negative 13 cotangent x. Example number 4, we're going to factor this, but our challenge is there's 2 different functions, which wouldn't be too bad if we could factor out a common factor like we did in a previous example. We don't have that option here. So what we're going to need to do is to get this to be in terms of one function. So somehow be able to change this all into one function. And usually the one that's going to be easiest to change is going to be the one that's squared, because that's going to bring in Pythagorean identities. And I'll be honest, I don't have these memorized. I do know the basic one, and then we can manipulate from there. So in terms of t's, I do know that sine squared t plus cosine squared t is equal to 1. And to create tangent, we would divide this by cosine squared t. That actually makes tangent squared t. So I'm going to do that. If we divide everything by cosine squared t, we're going to get tangent squared t by the Pythagorean identity, or by the quotient identity, plus 1 is equal to, and then 1 over cosine squared t, reciprocals would be secant squared t. So we can replace secant squared t with tangent squared t plus 1. Now we still can't factor yet because we're going to need to distribute and combine like terms. Make sure it's in the correct order. Squareds, tangent t, constant. Now we're ready to factor. It's got to be in the front. 2 tangent t and tangent t, something like maybe a minus 3 and a plus 2 or something like that. Turns out that it's going to be 2 tangent t plus 3 times tangent t minus 2. Kind of check this out. We're going to get minus 4 tangent t plus 3 tangent t is negative 1 tangent t. And there it is. All right, example number 5, simplify the expression. One strategy can be to get everything in terms of sines and cosines. So if we go that direction, we're going to want to change tangent theta. And that would be using the quotient identity, sine theta over cosine theta. So, quotient identity. Then we can multiply these, and then we're going to want to do some addition. And we're going to add, well, we got a fraction, so we're going to need common denominators. Cosine theta is going to be the common denominator, so we're going to need to change this expression so it's something over cosine theta. So multiply top and bottom by cosine theta. And when we do that, we can add the cosine squared theta, because we're going to multiply top and bottom by cosine theta, plus the sine squared theta, multiplying these two, all over the common denominator. You should recognize that. That's Pythagorean identity. This is 1. And now we have a reciprocal situation where we get secant theta. So we want to simplify as far as we can go. Example number 6. There's going to be times where we're going to take some expressions like this and just kind of add them and maybe simplify beyond them. So again, we're going to need common denominators. We're going to need a 1 plus cosine theta. We're going to need a 1 minus cosine theta. So the LCD is the product of those two. That means this is missing 1 minus cosine theta, multiply top and bottom. This one's missing 1 plus cosine theta, multiply top and bottom. And we are adding. We simplify up here. Cosine theta is going to cancel. We're going to get 2 over. We can multiply this as well. That's an identity. Pythagorean. That's sine squared theta. And then once again, we have a reciprocal situation. We can flip this up as its reciprocal. 2 cosecant squared theta. Example number 7, indicating this is leading to calculus. We want to take this expression and rewrite it so that it's not a fraction. And the benefit to that is doing some calculus on this would be pretty challenging, whereas if it's not a fraction, it might be a little bit easier to do. So really our situation here is with the denominator, and if we're trying to fix a binomial denominator, a lot of times the strategy we might want to try is the idea of conjugate. So with 1 plus cosine x, I think I might want to try to multiply top and bottom by 1 minus cosine x. The conjugate. So easy multiplication on top, on the bottom, that's a difference of squares, so we're going to get 1 minus cosine squared x. No, we don't have canceling here. That would be highly illegal. But we do have an identity, sine squared x. And now what we could do is we could distribute this division. Take both of the terms on top and divide them by the term on the bottom. That doesn't work in the other direction. We could not split this up as 1 divided by 1 plus 1 divided by cosine x. It doesn't work when the denominator is the binomial. It does work when the numerator is. So we're going to split it up, divide it both by sine squared x. And then we're going to see if we can use some identities. We've got 1 over sine squared x, so that would be cosecant squared x. And then you might notice that I did split this up as cosine x over sine squared x. I split it up into a product of two things, each with a separate sine x as denominator. In which case, this is cosecant x, and this is cotangent x. And we don't have a fraction anymore. Example number 8. Another leading up to calculus. We're going to use substitution. So it kind of tells you what to do in the problem. We're going to assume that theta is in the first quadrant. We want to write this expression as a trig function of theta based on our substitution. So we will begin by replacing x with 5 sine theta. And it does need to be squared. And the next part is the key part. We are not allowed to distribute a function. We cannot square root this minus square root this. What we can do is factor this. There's a common factor of 25. Let's factor it. Okay? It's going to turn it into a product, and that's going to be a lot easier to actually perform the square root part. Oh yeah, 1 minus sine squared theta. That's an identity. That's a Pythagorean identity. Now, because it's a product, we can square root both parts, as there is a property for square roots and other radicals. But the square root of the product, a times b, is the square root of a times the square root of b. So we get the square root of 25, 5, square root of cosine squared theta. In this case, because of this condition, saying, hey, theta has to be in quadrant 1, where cosine is positive in quadrant 1, we would just get 5 times cosine theta. If we did not have this condition, when you're taking the square root, you have to get a positive answer. To force cosine to be positive, we can just put it in absolute value bars. We don't have to do that because we had this condition. Without this, we would need the bars, because when you take square root, it's talking about principal square root only. You can only get a positive answer there. Example number 9, rewrite this log expression as a single logarithm. Simplify. So we're going to have to use from chapter 3 log properties. Log, in this case natural log, something plus natural log of something. That's the product property. So one single natural log and multiply them together. And let's see if we can simplify this. Again, maybe it helps to get in terms of sines and cosines as a strategy. So secant is reciprocal identity, 1 over cosine theta. Cotangent is quotient identity, cosine theta over sine theta. And we could cancel those out. We have 1 over sine theta. We can simplify that as a reciprocal identity. So the natural log at the absolute value of cosecant theta. Why would we need the absolute value? Remember, we're only allowed to take the natural log or other logs of quantities that are positive. Cosecant theta is not always positive. So to force it to be positive, here's where we need the absolute value. That's it for today. I'll see you next time.